Hey, welcome back. So we're going to quantify the amount of energy it takes to vaporize something. So remember, vaporize, right, is where we're taking a liquid and we're turning it into a gas. And so what this is, right, is it's a measure of the strength of the intermolecular forces because the liquids, right, they're stuck next to each other. And when they form a gas, right, the thing about gases is that they're so far apart, they no longer have any interactions at all. So we are measuring the heat. Okay, I shouldn't really say heat, right? But I should say the enthalpy change, which corresponds to the heat under conditions of constant pressure. And if you're in physical chemistry, under no additional work like electrical work. But we're just going to go ahead and say that delta H is a measure of the amount of energy or heat it takes to vaporize. So at 25 degrees C, we can go ahead and we can measure a bunch of these values. So if we take our friend water, for instance, and we take water and we vaporize it. That is really just saying we are converting, say, a mole of water into a mole of water vapor. We're doing it at 25 degrees C, so this isn't technically boiling. And if you leave a cup of water out at room temperature, you know that it will eventually turn into water vapor. It will disappear. Delta H for that process is 44 kilojoules. So what we're saying is that every mole of water here that evaporates at 25 degrees C is going to take 44 kilojoules. And it's positive, right? So that's endothermic. It requires energy. Whereas if we look at, say, a much larger molecule, so like acetone, C3H6O, and you might say, well, it's bigger, right? So it's going to have stronger interactions. The answer is not that simple. It turns out that, well, we can measure it. Delta H of vaporization for acetone is positive 31 kilojoules per mole. So it's taking much less energy, right? So it's taking 13 fewer kilojoules per mole to evaporate at 25 degrees C. And if we take a molecule like C5H12, so C5H12, so that's something like pentane and or lighter fluid or something, right? And we vaporize it, so essentially we're just converting it into gas. It's going to take hardly any heat at all compared to water, right? It's something like positive 26 kilojoules per mole. And that's very patriotic there, red, white, and blue. Didn't think of that. So the question is why? So why is water much, much harder to vaporize than acetone, which is a little bit harder to vaporize than lighter fluid? And the answer is, by this point here, you should know, it's all about the intermolecular forces. So in the case of water, you've got London dispersion, you've got dipole-dipole, and you've got hydrogen bonding. Whereas in acetone, we drew the structure in the last lecture, you've got London dispersion and you've got dipole-dipole. Whereas if you look at something like C5H12, unfortunately, it only has London dispersion. And so you can see that those intermolecular forces, right, the more you have and the stronger they are, the harder it is to break apart. And we see that the enthalpy of vaporization, or the heat of vaporization, takes a lot more energy when you've got a lot more and stronger intermolecular forces to deal with.